Hi, my name is Emile Timothy, and this summer I worked on identifying chemicals through dimensionality reduction, and I did this with the mentorship of Charles Steinhardt and Morten Hansen at the Niels Bohr Institute at the University of Copenhagen. So, to set up the story, there is an undeniable need to provide safe water across the world. With the rise of pesticides and heavy metals, water contaminants have grown in complexity, and the process of determining water contaminants has also had to evolve. And so, scientists currently use targeted analysis to search for water contaminants, where a targeted analysis is when a sample is tested to determine the presence of a particular substance. However, a sampling issue is born out of this. How do scientists know what substance to look for if they have never seen it before? So, to put this problem in perspective, scientists know to test drinking water for chlorine because chlorine is bad and can be found in water. However, if some newer compound were to infiltrate a water supply, scientists would never know to test for it just because they have no reason to suspect it to be found in water and because they might never have seen it before. So, to solve this problem, we studied untargeted analysis, which is when we conduct a broader search to identify both known and unknown chemicals in the sample. However, untargeted analysis is such a broad term that we still do not know how to specifically do it. So my goal over the summer was to give on-target analysis some definition through which we could solve the sampling problem and therefore this larger problem pertaining to water safety. So how do we measure a sample to record enough information to tell us which substances are in it? Humanity's most cost-effective answer is the mass spectrometer. So how does a mass spec work? It takes in a sample and vaporizes it. It then breaks up this sample using electron beams into ionized fragments. These fragments are then accelerated in an electromagnetic field, which causes them to deflect onto a detector, such that the lightest fragments are deflected the most and the heaviest fragments are deflected the least, allowing the detector to measure the mass to charge ratio of each fragment. And the detector also measures the force that the ionized fragment exerts on it, therefore measuring the relative abundance of each fragment in the sample, which it then calls intensity. And it represents this information in a mass spectrograph. Therefore, we now have a way of transforming a physical sample into some digital information while still capturing all the relevant information in the sample. So the question we're trying to answer is it possible to reverse engineer the process of reading mass specs? That is, can we take in a mass spectrum corresponding to an unknown sample and find out exactly what functional groups are in the chemical or even what the full chemical is? Therefore, we now reduce the question to a machine learning problem and we can show that it is still a hard problem. So before I tell you why this is a hard problem, I will briefly talk about our data set and our data processing. So it's the European Mass Bank. It's got a library of about 18,000 compounds. We quality checked each compound to ensure that it had at least 5 peaks. And it consists of an ecosystem of databases developed at various European universities and research centers. And an important question now is how do we compare different spectra? So in the example here, these spectra are as different as they could be, but in their raw form, it's hard to quantitatively determine how different they are. And this problem gets amplified since our database uses many smaller data sets, each of which uses different data and posts these data differently. And so with a different number of points and a different range of master charges. So we really do need a way to standardize the data and to therefore compare them. So it's commonly said that binning is sinning, but really in this case, it was essential that we discretize the spectra despite any small downgrade. So we bin the data into 800 bins by collecting small groups of master charges and summing the intensities in all of them and discretizing the data. And now if you ask me what is the intensity of the peak at the master charge of X in the spectrum of Y, I can give you a number, which is good. And since this is now conclusively a machine learning problem, it is useful to analyze the impact that binning the data had on its dimensionality. So we initially had a dataset with 18,290 variables, where each variable corresponded to a spectra, and we reduced it to a dataset of 800 variables, where each variable corresponded to a bin and was a function of the spectra. And this reduced the size of our dataset by 95.6%. So back to why this is a hard problem, and to remind you, the problem is to reverse engineer the process of reading mass spectra, that is to take in a spectrum as an input and decide exactly which chemical it corresponds to. The typical machine learning approach would be to say, look, I have a data set with thousands of variables, let me just fit a neural network on it, and that will solve our problems. However, the problem with neural networks here is that similar compounds have dissimilar spectra. So while a neural network would attempt to optimize a continuous loss function, there really is no loss function to minimize and no continuous distribution that can be created. So while this does not make the problem unsolvable, it does mean that we have to look at other machine learning models. And so with 800 variables, we can represent the dataset perfectly. Is it possible to then reduce that number of variables while still maintaining a sufficient degree of integrity of the data? And we started by looking at principal component analysis, or PCA for short. And PCA assumes that every point in the dataset can be written as a linear combination of a certain number of orthogonal basis vectors, and it then tries to find the optimal number of basis vectors to represent every point in the dataset. So in this example here with 2 dimensions, there are an infinite number of choices for 2 orthogonal bases, but the choices that best minimizes the coefficients of the linear combination would be these vectors. And to be clear, if we use PCA in our dataset, we're assuming that each compound is a linear combination of atoms or functional groups, each of which can be represented by a basis vector. So we ran the principal component analysis on our dataset, and we ran into many problems. Firstly, the basis vector had negative coefficients, which does not make sense, right? Like, what does negative intensity even mean? And secondly, while the basis vectors had been optimized to minimize the error mathematically, they were not physically meaningful because we're looking for basis vectors that correspond to actual physical atoms of functional groups, so they need to be in the right orientation. But the vectors that the PCA spits out can really be any possible rotation of those basis vectors, and we don't have enough information to rotate these rotated basis vectors back into place, which means that the basis vectors that the PCA spits out, if they are physically realizable, are impossible to extract. So we then moved one assumption down the ladder and used non-negative matrix factorization, which no longer assumes that the basis vectors are negative and forces them to be as sparse or as empty as possible. So with non-negative matrix factorization, we can factorize our spectral matrix into a matrix of n columns of weights and n rows of basis vectors, where n is the number of basis vectors. Ideally, we want n to be as low as possible, but to produce a w and h such that their product is close enough to x. And the only way to optimize n is experimentally. So we ran the non-negative matrix factorization on the spectral matrix for various number of basis vectors, and we found that around here at the 120 component mark, you do not get a significant decrease in error if you continue increasing components. And at some point, the error even increases slightly. So we made the executive decision to choose 120 basis vectors. So what this means is that these 120 basis vectors would each ideally correspond to some atom or functional group, which could be building blocks to every compound in the dataset. And 120 variables is a lot fewer and therefore a lot better than the initial 800 variables we had, both of which now represent the same thing pretty similarly. And at this juncture, it is useful to again analyze the impact of dimensionality reduction on the dataset. So when binning the dataset, we reduced it from 18,290 variables to 800 variables. And now when doing the non-negative matrix factorization decomposition, we reduced the variables further from 800 to 120, creating an overall percentage decrease of 99.34%. And we can also additionally look at our reconstructions. So by virtue of the linear algebraic nature of the non-negative matrix factorization, we can multiply column I in the weights matrix with row I in the basis matrix that we get from the algorithm. And this gives us the reconstructed spectra of I. So you can actually compare specific spectra with their reconstructions, with the purpose of reconstructions was to capture the entire data set by discarding the unimportant variables with static information and keeping the important information with dynamic information that changed between spectra. So in this case with this compound, here is the actual spectra, and here is the reconstructed spectra, and we can see that they're really quite similar. In this example with this compound, the spectra are again somewhat similar, but with a few noticeable differences, primarily in the scaling. And we can even compare the full spectral matrix with its reconstructions by giving every value a color in the continuous domain. So here's the actual spectral matrix, and this is the reconstructed spectral matrix. And the fact that they look so similar is good because it means that we can keep going. So the question that follows then is, are the NMF bases physically meaningful? And again, the bases would ideally correspond to atoms or functional groups, so we would like to see each basis vector have a very small number of peaks, maybe even just a single peak when you plot it. So we extract the bases that the NMF gave us to see if they were physically meaningful, and then lo and behold, we found that every single basis vector had a very small number of peaks, as shown here in these figures. Coincidence? I think not. So that's an excellent sign, but can we extract anything useful from that? So I wrote the following algorithm named searcher to tell me the mass to charge of various atoms of functional groups. So how it works is it first finds the reconstructed spectra of all compounds with that token, then averages all the intensities across the compounds with that token. It finds the bin, or the mass to charge that contains the highest intensity, and then it returns that bin. And most of the time, the mass to charge, or the bin returned, is equal to the atomic mass, which is already known from many tokens. So this becomes a really good statistical test to tell us if you're onto something. So when we ran the searcher algorithm with the oxygen molecule, we found that the algorithm actually converged to a specific basis vector, which meant that a single basis vector corresponded to oxygen. And it also extracted a mass to charge value of about 31.14, which is pretty close to 32, which is the actual mass of oxygen. So note here that at no point did we ever tell our algorithm that the atomic mass of oxygen was 32, but yet it was able to learn it on its own. And then when we ran the searcher algorithm on chlorine, we found that the algorithm produced an incorrect mass to charge of 22.87, whereas chlorine's is really about 35.5. However, we still speculate the algorithm is behaving correctly since 22.87 is the atomic mass of sodium. And we know that the data collectors dissolved most of their organic compounds in brine, which is concentrated sodium chloride, and that some of these sodium ions could have easily gotten picked up in the detector, which is why they're showing up now. And we then ran the algorithm again on carbon and hydrogen and found that they yielded the exact same results. So the algorithm predicted that their mass to charge would be 31.42, which is the exact same thing that we got with oxygen. However, we suspect again that the algorithm is actually behaving correctly in doing exactly what we told it to do. But the problem here is that carbon and hydrogen both have a spectrum that is being dominated by that of oxygen, and therefore oxygen's atomic mass is being shown here, with 31.42. And this is also a hard problem, which lends itself into our future works. So, one future direction for this work would be to understand how to remove dominating spectra from the database and reevaluate how to identify the suppressed spectra. And sometimes the presence of specific atoms, such as chlorine or oxygen, can sometimes have a nonlinear effect on spectra, and this changes the entire spectral landscape. So, another direction would be to possibly go further back and look at different decomposition methods, which incorporate some of these nonlinear dispersion effects, such as the Tucker decomposition. So, through this and future research in this direction, one might reverse engineer the process of reading mass spectra to identify chemicals, and through that, solve the question of identifying chemical substances and solving one of the world's most daunting practical problems. Thank you.